Okay, good morning, guys. Thanks for joining in the session. So, I'm Rakesh. I have with me Dinesh, who is known here already. So, we're going to talk about I/O patterns, which is a very interesting topic in the whole, Postgres database technology itself. The reason we picked up this topic, obviously, because we do a lot of I/O stuff with our HPC offerings at Tessell as well. So, we have built some technologies to make I/O, provisioning or the whole performance related stuff around IOPS more and more available at a much lower cost. So we're going to start with that discussion early, and then we'll deep dive into different IO patterns, right? And what all things you should keep in mind while you're basically running different patterns, what all things you can think of debugging, right? So all of those different patterns we're going to cover today in the talk. So I have Dinesh here. Probably he'll give a short, brief introduction, and then we'll take it forward from there.
Hi everyone, good morning. Myself Dinesh, and I'm working as a principal architect at Tessell. So these are some few of my books which I have co-authored. I especially talk about only Postgres and some kind of tips and tricks in how to write better optimized PGCQL, that is a server-side programming language for Postgres. And there are few open source tools which from Tessell we open sourced, like the tools like Peter and HammerPost, and which I'll talk about.
Thanks, Dinesh. Yeah, so I'm Rakesh. I'm a solution architect at Tessell. I build products and platforms around Tessell, on Postgres extensively in IoT space, financial, e-commerce. And now we'll basically talk about a bit about what we are doing at Tessell to actually solve this IOPS problem that we have seen with managed databases, especially in cloud. So we are actually, we have a system which is called as Tessell HPC, which allows you to run databases on NVMe-backed storages, which are ephemeral in nature, but we have some technologies that we have written, which allows you to convert this into a high-performance, durable databases, right? So when on any of the public clouds, when you use ephemeral storage like NVMe or flash drives, as soon as you switch it off, it goes off. What we have built is, here is a patented technology which allows you to actually make sure, even if you're running databases like Postgres or even MySQL, any other database, to have a zero data loss system. This also helps in completely cutting down your IOPS metering, which you actually occur a lot with managed databases. We have some benchmarks which are available on our website, which actually talks about how you can better your IOPS if you have massive hungry IOPS workloads that you're running from the application side. The details about it is also available that I'll share some links later on. And to deep dive into IO session that we have now, this is what you expect today that we're going to cover. We're going to do a quick primer for people who have some knowledge on IO and what is IO in a database, talk about it a little, and then what are the different components, different patterns that exist out there, right? So I'll hand it over to Dinesh. Yeah, so none? So I'll hand it over to Dinesh now, and we'll talk about all of these things that you see out that we have planned for you. Thank you.
Thank you, Rakesh. Thank you so much. Rakesh, you can talk maybe offline if you want. Okay. So today's session is all about like IO patterns in Postgres, and this is a case study what we have done. Like in Postgres, there are few memory components and few processes, right? So when you make any SQL statement like insert or select or DML statement, right? So which process is actually making IO? Like, what is that process? So when you do insert, which process is making the IO? Whether it is a client backend, the connection of the Postgres, or the val writer, or the background writer, right? So this is the case study. Again, like we just want you to present you like yeah, which process and which memory components are leading to I/O. So we all know like I/O is an input and output operation, and if there is any DML like insert, update, and delete, it's a write operation, and if it is a just read, right, that's just like reading the data from the disk. So where actually IOPS happen, right? So here you see we have a client backend. The client backend stands for the connection what application makes to the Postgres, right? And we have a component like shared buffers, and we have a OS cache, and we have a disk cache and a physical storage, and there is the IOPS where it is coming into the picture, like it is between the shared buffers and then underlying hardware. So we are skipping their OS cache. So yeah, we come to that point. So it's just an overview like where the IOPS is happening. It's between the memory and then the actual disk. So just overview like what memory components we have in Postgres. That is, we all know like shared buffers, val buffers, workmem, maintenance, and there are logical decoding workmem, temp buffers, right? And there are some processes in Postgres that is like a backend client, val writer, check pointer, and maintenance maintenance workers, and auto vacuum workers, and finally we have val senders. So now the agenda of this talk is like to display to present which process is leading the is doing the I/O whenever we do any DML or any SQL query. So yeah, so I think we can skip this slide. I think yeah. Okay. So to perform this I/O case study, we used strace and we used I/O catalog tables extensively to see which process is actually making the I/O when we do any operation. So let's start with the first I/O pattern. So here we are trying to do a single DML statement. It's a very single normal insert statement, right? So the normal insert statement comes from the client backend. The client backend is the connection what the application makes to DB, right? So that goes to shared buffers. You just take an example like sample insert statement, simple insert, just insert A, that's it, right? Don't take big values, just inserting A. And the value what we are trying to insert, it goes to shared buffers, and shared buffers to val buffers, and val buffers to, it goes to the val file. So here the I/O is doing the val writer. Even though you do a single insert operation, the val writer is the process, is doing the I/O for you. Any single operation, right? So here the catch is like the val writer only do the I/O in the case of synchronous commit. Majority of the DBs have the synchronous commit, right? So if you have that synchronous commit parameter enabled, then val writer is the process which actually makes the I/O for the single insert operation what we did. Single A, right? But it do a bunch of I/O. So sometimes client backend also do I/O because you are trying to insert the data into the table, but the table has to be see where the free space, because we have this vacuum, right? So the client backend go and do the relation file free space map file. So the client backend makes an I/O plus the val writer makes an I/O for single insert operation. This is one pattern, and yeah. Now see we are inserting bulk, right? Maybe trying to insert like 1 GB of data, 1 GB of messages, right? So, and even we have a synchronous commit is on. So here the I/O is coming from the val writer, and anyhow the client backend, which actually reads that free space map file, and the data what the client backend push to shared buffers, right? So if the shared buffers are not sufficient enough, they have to be flushed out. They have to go to the underlying, right? So here the IO comes from the client backend, which is actually busy in inserting the data, and also shared buffers are not sufficient enough. It has to flush the data to disk. So that job is done by the client backend, the connection which is made to database. And as we are pushing the data continuously, val writer also busy, right? Like here we have two processes continuously pushing the continuously generating the IO. One is the client backend, the other one is the val writer. And here the point is like if we go beyond that 16 MB val size, val writer takes the responsibility of switching and creating more val files, right? It's not just pumping the data, but it's also taking care of managing the val files. So here the IO comes from client backend and val writer. In the case of if you do bulk insert, and assuming that whatever we are inserting, we are committing it. Okay, there is one more case where we do rollback. I think both are same. We have, yeah. So if the shared buffers are not full, that's fine. The other process will take care. If the shared buffers are already full, then the client back into the IO. Right. So this is another pattern where we have synchronous commit is off. A simple statement, a simple DML statement, insert or update. So the data actually goes to shared buffers and val buffers, but client backend only do that FSM read IO, and the majority of the heavy lift is done by the val writer, and there is no IO from the client backend, right? So if you disable this synchronous commit, you always have the better query response time, because the client backend is not involved in any of the IOs. Most of the even the val writer will periodically flush the data to the val file. Right? So this is the one pattern where we have IO from val writer only if we have synchronous commit parameter is off. So in this case, we don't need to immediately commit the data to underlying disk. Right? That's where the synchronous commit comes from. If you turn it on, if you do commit, the data has to be in the disk. If you turn it off, data can be memory. Eventually, it can go to the disk. Right? So this is one pattern. And again, like if synchronous commit is even though off, if you do bulk update operations or bulk insert operations, still the val management will be done by the val writer. It has to create a next 16 MB of val file, right? It has to do a bunch of stuff. So here the val writer is the guy who do the IO. Okay, so this is, yeah, any questions? Any questions as of now? Right, there's another pattern for it. Yeah, we'll talk about the PG writer as well. Any questions? I'll come to that point. Correct. Shared buffers is the memory area. It's only dedicated for the PostgreSQL connections, right? Which is it's a common area where all connections shares the data. Yeah, so you will understand that there is one more pattern which we are going to talk about. Okay. So this is another pattern where you are inserting the data. It's a small data, and it's not a bulk, simple data, but you have your shared buffers already full. Right? Shared buffers are already full, but you are trying to insert a small data. So now it is the client backend or the connection responsibility to free some of the buffers in the shared buffers. Right? It is the client backend, the connection which makes the Postgres, which makes the connection to DB, application connection. That is responsible to clean some of the shared buffers. So there, client backend indirectly doing some I/O because it has to put that data, whatever we're inserting, like A or B, into the memory, but there is no memory for it. So it will flush some of the data to underlying disk. And eventually we have the val writer. So here the I/O is coming from, directly from two processes, that is client backend and val writer. So here the relation I/O stands for whatever the buffer, the client backend is flushing, right? So that relation I/O is caused by the client. So in this case, we get a very less throughput or less response time from the client because it has to do additional job. It has to clear some of the shared buffers or dirty buffers to fill the incoming request. Okay. So another I/O pattern here, we talk about temporary tables. So when we create any temp tables inside Postgres, all the temp tables don't go to val buffers because temporary tables don't get replicate. Yeah. They don't go to val buffers. So there is no I/O from the val writer. So we are good there. Also, the temporary tables don't go to shared buffers. The data, because shared buffers is the common area for all the connections. But the temp tables, they are scoped to that session only. Only that session, once the session is gone, the data, whatever this guy created, that will be deleted as well. Right? So in this case, no I/O from val writer, no I/O from any of the other processes. It's the pure I/O from your client backend. It goes to temp buffers and it goes to relation I/O. And one more thing, on temporary tables, there won't be any auto vacuum, there is no checkpoint, nothing. Right? It's unnecessary I/O because it's only created for that session. Right? They also like auto vacuum, checkpoint, they also don't trigger on the temp tables. So temp tables you can always assume like it's a pure I/O which is happening in the DB from your client backend. Right? Any questions? Okay. Next, another I/O pattern. It's a simple SQL query. Take a simple SQL query, and this I think we all know it. Like actually, when the SQL query executes, it fetches the data from the underlying relation I/O, and it plays into the shared buffers. It's like a cache. It's a Postgres cache. You can treat that as a Postgres cache. And if you don't have any sufficient work mem for the incoming query operations like joining or order by, then it is client backend responsibility to create all your temp files. The connection what made to Postgres, right? That guy will create all the temp files. So in the case of less work mem, the client backend responsible to create the temporary files, which leads to most of the I/O. And also in this case, we will get very less throughput from the client backend because it has to deal with all these temp files, right? And also once the client backend is done, it has to also do the cleanup job. It has to delete all the temporary files which it got created. Sometimes we see in the production the temporary files like 10 GB or 20 GB, and it has to clean those as well. So the I/O is coming from the client backend. Any questions here? Any questions? So another pattern is whenever we have this maintenance operations like vacuum or reindex. So these are like I/O hungry operations because we run this operation on an entire table. For example, I want to run vacuum only some portion of the table. No, it don't happen. Even the reindex, when you do, you have to perform on the entire table. And if the table is like few gigabytes, it has to read, and then sometimes it has to generate some kind of free space map files. It has to touch each and every tuple. visibility map. So there's a bunch of stuff. So these are the IO hungry operations always. Also, it will generate more of the val data. So val writer comes into the picture. So we have the client backend, the maintenance operation, whoever triggered these maintenance operations, and then the val writer. These two generates most of the IO. But they don't happen regularly, but whenever we do, it's a kind of hitting the most of the IOPS, right? Yeah, that's what it is. Okay, so another IO pattern. So here we have a special process called background writer, BG writer. We call it as a BG writer. So the job of BG writer is to free some of the shared buffers and make them available for the incoming connections. So it's a kind of schedule, kind of maintenance. So we can control that. The schedule, whatever I'm trying to say here, right? We can change the schedule. Like it has to trigger for every 500 milliseconds or 200 milliseconds, right? We can schedule that. But the job of it is always to make sure the shared buffers are having kind of sufficient shared buffers for the incoming connections. It will do some kind of cleanup job. I would say, like in simple terms, this guy is a kind of auto vacuum for your shared buffers. You can treat that way, right? So this happens periodically. This happens periodically. Even though the DB is idle, sometimes Postgres will the internal process, right? Auto vacuum or stats process. They'll try to update the catalogs. All the catalog metadata, catalog updated data that will be in the memory, in the shared buffers, that will be flushed by the BG writer, right? Okay. So here is one more interesting pattern, like where client backend is doing bulk DML, right? And your shared buffers got full. And we have the val writer anyhow, that is generating the IO. And BG writer also will try to clean some of the shared buffers, right? If client backend is not getting sufficient shared buffers, then it is client backend responsibility to clean some of the buffers. So here we have three processes which generates the IO in this case, right? So here the culprit is like the shared buffers. I would take the shared buffers as a culprit. If you have very less, then the BG writer will come into the into the action, and then eventually client backend, which is doing this bulk operation, also need to do some kind of flush. Right? So here you see we have three processes: BG writer, val writer, and client backend. These three are making the IO. Right? So if we have sufficient shared buffers, I think we're good. If we don't have it, then we have three processors running ready, right? Yeah. I think okay. Next. So next we have the checkpointer. We all know, like checkpointer is the one which actually flushes majority of the shared buffers, all the dirty buffers, from shared buffers to the underlying tables. So for example, I have dirty buffers for table A and table B, or relation 1 and relation 2. And checkpointer is a maintenance process, like it happens periodically, like for every 5 minutes or 10 minutes. And checkpointer responsibility is to persist the buffers, whatever we have in the shared buffers, into the tables, right? So whenever checkpointer is triggering, it will also do some kind of val cleanup. So we have these settings, like how much of val files we have to keep inside Postgres. And that val rotation has to be happen. So it happens every checkpoint. It happens after every checkpoint, right? Yeah. So this is the one pattern what we have. So again, it is a maintenance, like it happens for every 5 or 10 minutes or the scheduled time. Or it also happen if you have this val size which you have configured, right? So this happens Yeah, this happens periodically, right? Yeah. And one more thing is like, for every checkpoint, make sure if we have the full page writes parameter is turned on, right? So after the checkpoint, always expect more IO because of this guy, full page writes. If you have very less checkpoints, like for every 1 minute you are doing the checkpoint, then after checkpoint to checkpoint, the first time Postgres do the full page writes. So if this parameter is on, then there will be more IO. Even though we are updating one value, 1 byte, it actually do one block. Like entire page size is 8 KB, the block size is 8 KB. So even though we are updating one value like A or B, single byte, but it actually do 8 KB. So always expect more IO after checkpoint if you have this parameter is on. Any questions?
Here, there are multiple processes cleaning the shared buffers, right? So sometimes checkpoint is cleaning up, and sometimes client backend is processing, cleaning
Right.
up these shared buffers.
Right.
Sometimes wall buffers.
Correct.
Is there any conflict can happen, or any if suppose wall writer clean the buffers, so other process will come to know that okay, I cleaned up the shared buffers. Okay, there is free space to write in shared buffers. So if there is a mechanism to work.
Yeah, we have this lightweight logs based on, so these are all like 3 processes, right? Val writer and then checkpoint and BG writer, right?
Yeah.
So it's a kind of, they're all running for the shared
Space.
memory,
Okay.
and they all have to have, kind of serialization there. So they all communicate via lightweight logs or some kind of mutex. Yeah, the process has to be synchronous. It has to happen like one after the other.
Okay.
It can't use a mutex. Lightweight logs. Yeah. Correct. I don't know what mechanism internally it is using, but I'm just trying to say like, the action has to be serialized. Yeah.
And what is the ideal value for checkpoint intervals?
Which one?
Ideal value for
Checkpoint interval by
Yes.
no, there is no that number. No, there is no silver bullet point for that. No.
Okay.
There's no silver bullet. Yeah. We have to see.
Okay.
Right? Yeah. So checkpoint whenever we do, if we have more shared buffers in that TEED, right, then there will be more IO as well.
Okay. One thing. So, for example, my database is 2 GB.
Huh.
Okay, I configured 2 GB of shared buffers.
2 TB.
2 GB.
2 GB.
2 gigs.
Uh-huh.
My database size is 2 gigs.
Uh-huh.
And I configured shared buffer size is 2 gigs.
Uh-huh.
So, will there be any impact on the database? Because entire database can come and sit in the shared buffers, right?
How well you are using the 2 GB? That's the question. Like, we can put entire 2 GB of DB in the shared buffers. That's fine. But how well you are using it? Are you doing any DML, the frequent writes?
Yes. Doing frequent.
Right. Uh-huh.
Doing inserts on multiple cities. DMLs is happening on the database.
Correct.
It is frequent. Every day it will happen 1 hour and 30 minutes like that.
Right. Yeah. So I think we have to measure that behavior.
Okay.
I can't tell like, set some value like.
No, is it good to have like that, or it is bad?
It's application behavior we have to see first of all.
Okay.
It is not like if I say go ahead, then that's not the right answer.
Okay.
We have to see it first of all.
Okay.
Yeah.
Thank you.
Yeah. Yes. Full page writes if you turn off, yeah. Yeah, it's not a performance issue. So this parameter, especially full page writes, what happens is, after checkpoint, whatever block you are updating in the disk, it will write the entire page. So this is the safety of the page corruption. It's a safety, one of the safety features for the page corruption. Yeah. But there will be more IO, but expect more IO after checkpoint. Any other questions? Uh-huh. prefer that time-based checkpoints are the best, because how well to spread the checkpoint, like how well to write those dirty buffers, the checkpoint algorithm, that knows well.
At the size would also go up. Like it would be a frequent, I would say frequent transactions, and the val file we increase it to 10 GB or 20 gigs. At that time, the checkpoint when it does it, the load of it also would be increased, right?
Correct.
So
Yeah.
if we go with a longer time, still it will be the same problem we would be having, right? Continuous checkpoint, or else the longer part of the checkpoint also would be the same.
I've not completely got your question.
Okay.
I think I'll connect with you. Okay.
Sure.
Is that okay? Thank
Yeah,
you.
that's
Thank you. Okay, let me show some other patterns as well quickly. So other pattern is like, val sender. So we have this logical decoding support in Postgres, right? So we have multiple plugins supports the logical decoding. For example, any of the data what we are trying to insert or update or delete, if you configure any of the plugin, like the data has to go to a stream with a plugin called val2json or PG output. So these are the kind of plugins. So the data has to be in that format. So this is the work mem especially used by the val sender process. And if you are generating excessive data, and if you don't have the enough decoding work mem for the plugins, the data will be spilled. So, and again, the val sender responsible to generate the temporary. These are the temporary files only, right? So, yeah. Uh-huh. Memory?
You have the top box, right, where something underscore mem is always
Right.
there, If you go to all your last 15 slides,
Correct,
they have the
correct.
same pattern. So
Correct,
my
correct.
question is, how many allocators are working in the backend?
You mean to say these buffers, these work mem?
Every time you write that parameter.
Correct.
something underscore mem.
Understand. So
How many allocators
whenever
are-
you see mem, that is at the most of the time it is at the session level. So
No, I'm asking
how many only
memory
one process.
allocators are working?
Only one process. You mean to say allocator like a number of processes, or
Allocator is one who will go and eventually do a malloc.
the same process?
Okay.
The same process. Yeah. It's a per session. So you see here like shared buffers and val buffers, right? These are the common memory area. Yeah, these are like session level, per session level. Okay, any other questions?
Hello. Can you go back to the last slide?
This one?
Not this one actually.
This
yeah,
one?
this one actually.
Uh-huh.
So I just had out like, let's say we have a bulk DML or something,
Okay.
and shared buffer got full. It's in a
Okay.
transaction. Okay, begin and commit. Like we haven't done the commit yet. Shared buffers got full,
Correct.
and it flushes the data to disk. Okay, like that's the client backend's work to flush the data, right?
The client backend
But-
did the flush, yeah.
So data went to the disk,
Okay.
and at the end we do the rollback.
Correct. Yeah, there is one more good. Yeah. Right. So what happens in that case is, so I'll come back to this slide. This is the slide where client is doing bulk DML. We have shared buffers got full, and BG writer is also busy in writing the data. Val writer is busy. Client backend is busy. And now, if we issue the rollback or the connection terminated, right? The transaction got interrupted, right? So that is the double amount of IO. So we spend so much of IO here. Finally, the transaction got rolled back. All the tuples, whatever we inserted, they are dead tuples. Now, auto vacuum job comes in. It will do all the cleanup job. Whatever this IO did, it is auto vacuum responsibility to revert it back. That is double amount of IO. Auto vacuum will generate more val files. So that's what one suggestion is, like, don't disturb the bulk operations. That's one suggestion from me, because that involves double amount of IO. Whatever IO we have done, it has to be reverted.
What if auto vacuum is not enabled?
Auto vacuum is not enabled, no IO. But the tuples are deleted, they won't be visible. The tuples won't be visible, but that's a dead space.
Thank you.
Yeah, thank you. That's eventual, that's a maintenance operation again. Yeah. Okay, so other one is like, I'll be quick. This is the simple logger process, which generates the database system logs, like your database activity, auto vacuum statistics, checkpointer statistics, waits, right? So the log rotation, slow running queries, so CSV or JSON log format. So everything is done by this logger process. The IO is like, it's not negligible. It has to contribute as per your log settings. Right, so now we see the IO at the replica side. So on the replica, we have these processes like checkpointer, BG writer, val receiver, and then startup recovering. So these are the replica side, okay? So here always the IO will be generated by the val receiver process, because the sender is sending the data from primary. The receiver takes the data, push it into the underlying val files, right? Via val buffers. So here the val's receiver generates the IO. Sorry. Yeah. And also we have, on replica side, we have a checkpointer process, as I mentioned. So what this checkpointer process will do is, whatever the transactions which are applied by the startup recovering process, those will be in shared buffers. So the frequent checkpoint also happens on the replica side, and we call them as a restart points. So if you execute checkpoint, it don't do anything actually. So we don't control the shared buffers on the replica side. It is completely, the PG will take care of it. We don't control it. But in primary, when you do checkpoint, it actually flushes the data. But on replica, we don't control it. We don't have that control. So here is just a thing like, you can say like on replica side, shared buffers are always dirty. Always dirty, because it is keep applying the val files. So the shared buffers on the replica, they're always dirty. The frequent checkpoint or restart point, whichever is happening, right, is the responsible to flush the data to your underlying files. So you can say like in replica, startup process, and checkpointer and receiver. These are the three processes which always generates the IO, apart from your select queries, like the client backends. So this is just a demo, like, so on replica, we have created this extension called PG buffer cache to see how many dirty buffers are there. And we issued a checkpoint because we don't take that control, right? In replica, we don't take the checkpoint in our control. It will be in the primary only. So once we have issued the checkpoint, it did nothing. But we have the restart point happen. There you see in the log file, right? Here you see there is a restart point. So that actually clears the shared buffers, the dirty buffers on the replica side. But this restart point don't happen on the primary. Any questions?
You can open
How much time we have?
Done. 3 minutes.
3
Open
minutes.
for question.
Yeah, open for questions if you have any.
This is not a technical question, but on the second slide, you did patent spending.
Patent spending.
Yeah, NVMe. So yeah, for the NVMe, that system that we built on HPC, right? We have filed for 2 patents, which is the storage level technology that we have written, because we want to extend it to other database engines as well, right? So those are filed in US and they are up for approvals. And anything specifically that you're talking about, what is the status on those papers?
Does it target the file system, or does it target the cache, or does it target another storage engine inside Postgres?
It,
We talked that. We leave it up.
So you can come over the booth and
Any more questions?
anything else?
Anything? Yeah. This one?
Yes.
Uh-huh. So restart points are like checkpoints only. No, we cannot force it. On Replica, we cannot force a checkpoint. No. So this test case, sorry, this study, IO study, what we have done is on PG16. You can verify its behavior, right? So you just create some kind of tables on primary, insert some data. You come to Replica and verify the shared buffers. They're always dirty. Execute the checkpoint and verify the dirty buffers again. Don't do anything. Then let the checkpoint happen. The 5 minutes interval, whatever we have configured. And in the log file, you see the restart point. So they are in Replica, we always have a restart points, not the checkpoints. The restart points, the name come from, because even if the Replica is interrupted, maybe it is shut down in the middle. When the next time it starts, it knows from where it has to restart. That's where the name come from. Yes. Yeah. Any other questions? Yeah. It can, not a matter. Yeah.
I think we're about time.
It has to go to val and then apply, but still the dirty is there. Right? The sync happens between the val file to val file.
Thanks.
Any more questions?
Actually, you can go offline with the questions.
So any other questions, please visit our booth. We'll be happy to.
Thank you. Thanks,
Thank you so
Thank you
much.
so much.